So today we're going to be talking about the A-star algorithm. Now, the A-star algorithm is possibly one of the most useful path planning algorithms that's basically ever been invented. So today we're going to jump into what is the A-star algorithm, what it does, how it does that, and what are its applications. Let's go. So we're going to get started on some A-star applications so you can kind of know when and how it's being used. So the A-star algorithm is very useful anytime you're wanting to find the least path distance from some starting place and some ending place. And it's useful if you can find some representation of states between those starting and ending places. Now, one example of these starting and ending places is maybe like Google Maps. Your starting place is your house, and the ending place that you're trying to get to is the grocery store. And then we could perhaps situate the states between our house and the grocery store as maybe the intersections, and then the roadways as paths between those intersections. So in formal talk, this is a graph with nodes as the intersections and edges as the roads between the intersections. Now, if you ran a star on this graph, that is the road network, it would find the least path distance between your house and the grocery store. But one step further, because doesn't Dijkstra does that as well as plenty other algorithms. What A star does uniquely is it uses a heuristic to find that path faster or in fewer iterations than some of those other algorithms. Now let me give you another example. Say you had a game where you had some starting configuration of the game, and then you had a winning configuration that you were trying to get to. And you were trying to code in an AI that could solve this game. And so you could use an A-star algorithm to solve the game in as few iterations as possible, which in a lot of kinds of games, the state space can explode exponentially. So it's very important that we find the path, not eventually, but as quickly as possible.
Hey, special message. Please like and subscribe if you haven't already. Okay, back to A-star.
So those are some applications of A-star. Next, I'm going to go into what A-star does. Well, A-star uses something, it's called a heuristic. Besides that, it's just like Dijkstra's, and as far as its main mechanisms. But the heuristic gives it a hint of where it should look next in the graph. Now, Dijkstra's also has a hint of each iteration where to look next, but the hint is, let me look at the node that's closest to my starting place. Now, basically, this ends up generally being like a breadth first search if all the edge weights are equal, because it's just going to look one level out, and then 2 levels out, and then 3 levels out, which you can imagine if you're, say, trying to find a road network from New York to Seattle, Washington, that breadth first search is a very inefficient way to find that network, that path. So the heuristic, instead of just looking at where's the next closest to my starting location, the heuristic guides the search on each iteration of which node to consider next while looking for the ending node. And the heuristic does require some sort of global information. So a great example is like that Google Maps, and generally you could use the Euclidean distance between any intersection and where you're trying to get to. Now, notice that you can't only go by the heuristic to guarantee that that's going to be the fastest way to get to, or the fastest way to find the ending location. Now, this is because sometimes there's road blockages, or there's just not roads in the exact, as they call it, as the crow flies to your ending location. So you may have to divert, but it is a pretty good hint of where to go. Now, there's a kind of heuristic called the uniform heuristic, which is basically the naive heuristic, where you just assign a value of 0 to every node as the hint. And basically this gives you no information, but it's useful theoretically because you can show that if the heuristic is 0, then basically this algorithm just reduces to Dijkstra's algorithm. Now, let's talk a little bit about Astar, very high level, and then we'll jump into some of the pseudocode. Basically, you would think of it as we start with some starting node, and then let's look at all the neighbors. And let's see if any of the neighbors already have a parent, and what the least amount of distance in the past it's taken to get to these neighbors. Now, if we're just starting out in the algorithm, the starting node is going to, as it's looking at its neighbors, none of its neighbors are going to have a parent because they've never been visited before, and none of them are going to have a distance to them. So at the very beginning of the algorithm, we just assume basically that all nodes have a distance of infinity until they've been reached yet. But now that we are considering each node, we check to see if the distance of going from my starting node to my neighbor is less than the distance that the neighbor has recorded in it so far. And if we are just starting out, the answer is always going to be yes. Our distance to the neighbor is always going to be less than what the distance was before, because the distance was before infinity. So if that's the case, then what we'll do is assign the neighbor's distance to whatever the edge distance is between me, the current starting node, and along that edge. And we'll add those two distances. My current node distance, which if I'm the starting node, is 0, plus the edge distance to get to that neighbor. So we're going to assign that neighbor that distance. And then if that neighbor isn't in this list that I'm going to call the toExplore list, then we're going to add that to that list. So now we kind of have this growing list of neighbors that we're going to explore next. Now, once we finish through all the neighbors, or sometimes in these algorithms, you'll find that it says maybe like consider the eight neighbors, because sometimes we can have so many neighbors that it's not reasonable to consider all of them, but that's just an implementation detail. So once we've considered basically all the neighbors, then we need to move on to a next node and repeat, rinse and repeat. But how are we going to choose the next node? See, that's where Astar really comes in, because Dijkstra's would just say choose the next node, which hasn't been considered yet, or isn't in the current list of, or current cluster, and is the least amount of distance to where I currently am. And where Astar differs just slightly there is it says, yes, but also let's consider the one which gets us closest to our ending location. And remember and that's where the heuristic comes in, that's the hint. And so a heuristic, when the heuristic equals, a heuristic is normally a positive value, it doesn't have to be, but basically we want to minimize that heuristic. So think of Euclidean distance. So if Euclidean distance is 0, that means we're at the ending location. So we want to choose the node next to consider that minimizes that heuristic and gets us closest to our ending location. Okay, so we've just said, let's look at all the neighbors. Let's see if their distance is less than, or if we can get to them in less distance than they've been gotten to before. If so, we will assign their parent to me, their distance to my distance plus the edge distance, and then we're going to add them to the toExplore list. Once we've done that for all the neighbors, then we're going to look at, well, who of this toExplore list would be the most reasonable node to consider next, and we will choose that node which has the least amount of heuristic cost and the least amount of distance to least amount of distance from our starting node. So we're going to have a function named Astar. It's going to take in some start node and end node. It's going to have a toExplore list, which is actually we're going to implement as a priority queue, because that will allow us to always have the node which is the most relevant to us to explore next on the top. So now we're going to just go through and go pretty much to infinity. This line could just be also written as well true. However, it doesn't really matter because this is really where we're going to break out. Also, if a problem is solvable, A star is guaranteed to solve it in finite time. So here at this line right here is where we determine what node to explore next. And see that we just do the toExplore.pop. And this is because we've used a priority queue, which the top element or the first element of that priority queue is going to be the node with the least cost and distance. Now cost is where A star comes in. Distance, now that's basically something that you'll get from Dijkstra's, and that's if cost is just 0, if cost doesn't exist here, then you have Dijkstra's. So it's not that much different, just you have a heuristic. Now, this is the ending condition, that if our current node equals the end node, then we're just going to return the end node. We're done. And we can iterate then after we've returned this end node. We can look at the end node's parent and keep tracking all the way back to get the path, to regenerate the path that is the winning path from the end node to the start node. So then we're going to go through all of the current nodes, neighbors, and notice that when we start, we're going to start the queue with just the start node, and so when we do pop, the current is going to start with that start node. So the current here is that start node. So we're going to look through that start node's neighbors, and we are going to check if we're going to calculate some new distance, which is going to be the current distance. In the case of the start node, it's the start node's distance, plus some distance, edge weight, you could consider it edge weight distance between the current node and its neighbor. And if the new distance is less than the neighbor's distance, then we're going to do a few things. We're going to update the neighbor's parent to be me, which, remember, in the case of the beginning with the start node, then all of the neighbors are going to have an infinite distance beforehand, so this will always be true. The neighbor's parents so we're going to assign the neighbor's parents to the start node, the neighbor's distance to the new distance, which was calculated up here, and we're going to check if the neighbor is in the toExplore list, and if not, we're going to add the neighbor to the toExplore list. Now, let's consider a few examples. So let's say we started with a star algorithm, and this is our graph. Basically, we've chosen to implement that in whatever which way. It doesn't matter the implementation details of how we've chosen to implement the graph for the sake of this tutorial, but we have started here at the house, okay? And we're trying to get here to the grocery store. So we're going to call A star with 0, 0 as our starting node and 3, 3 as where we're trying to get to. So we're going to start by initializing the toExplore list with that starting node, which we've done here. And then we're going to pop the toExplore list, the top of the toExplore list, which is going to be the bit that we just pushed into it. And we're going to check if the starting equals the ending node, which we do right here. And does it? Nope, it does not. So we continue on. Now we're going to go through each of the starting nodes, which is the 0, 0's, neighbors. So we're first going to look at node 1, 0, which is this guy right here. And we're going to say, well, remember his distance was infinity, but we are going to check, we're going to first calculate this new distance, which would be the current distance, which, remember, the current distance of the starting node is 0, plus the distance to get to the neighbor, which, consider that these roads are all of distance 1 for simplicity's sake. So the new distance is 1. Now we're going to check, is the new distance less than the neighbor's distance? And in this case, 1 is less than infinity, so we're going to cross out the neighbor's distance and we're going to assign it a distance of 1. And we're going to check if the neighbor's distance, And then we're going to assign the parent to the current node. So the parents of every node at the beginning starts at none, but we will assign it the current node, the starting node of 0, 0. And we are going to continue to do that for all neighbors until we are done with all the neighbors. You can see here that basically the same path repeats for all of them. So I've taken this list now, and we are done with the first iteration. Well, there's one more thing here, that we need to add the two explorers, all of these nodes to the to explore list. So that's what I've done here. Let me redraw that. It's kind of gone away. So let's see. Oh yeah, so 0, 0 was on the to explore list, but it got thrown out when we popped it. And all of its neighbors got it added to the to explore list. It looks like this should actually be 0, 1. And don't mind that it's crossed out. Let me remove that. That comes later. Okay. So all of those are in the to explore list. These are not in the to explore list for now. Those come later. Okay. So we now have a growing list or graph representation of all our nodes. We have that you can ignore everything underneath this blue line for now, but we have through our first iteration, we have these nodes that now have a distance and a parent. And we are going to go through that entire iteration again and again and again, just once more to make sure it's clear. So next we need to, we have come to this line back up here. Well, it's not empty, which it's not. We're going to pop from the current, and remember we're going to pop the one with the least cost and least distance. Now this isn't maybe the best example because, well, all of these have the exact same distance, but let's look at which one has the least amount of cost. Now, if we're using the heuristic of maybe Euclidean distance or Manhattan distance, then we would want to we'd expect to pop this one or this one. So we are going to choose to pop the 0, 1, which is this one. Kind of arbitrarily, but because we could have chosen this one, but we're going to go ahead and pop that one. So that's why this crosses out. And that's what we're going to use as the current for next iteration. We're going to check if it equals the ending node. No, it doesn't. So we're going to go through all of its neighbors. We're going to check to its neighbors 1, 1, 0, 2, negative 1, and 0, 0. Now, the distance to most of these nodes have never been visited before, namely this one, and this one have never been visited before, so it's going to be similar as far as their distances are going to be infinity, and their parents before this is going to be null or null pointer or none. Now notice their new distance now is, remember 1, 1 has a distance of 1, 0, 1 has a distance of 1 already because of this line up here. So now we start by saying the current distance of 1 plus the edge weight distance of 1. So the new distance for all of these is going to be 2. And for most of these, we are going to go ahead and update the parent to be this, this current node. However, the one that we're not going to update the parent of is the starting node. It wouldn't make sense to update the parent because it's the starting node. So we correctly do not update the parent on that. Okay. So next we go through and we add all of those to the two. Well, let's see. Should we add all of these to the to explore list? Well, 0, 0 is not on the to explore list. Neither is this guy, this guy, or this guy. So yeah, we should add all of them, which indeed we do. I erased it. So we're going to add all of these guys. We're going to add 1, 1, 0, 2, negative 1, 1, and 0, 0. Boom, 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 boom. All right. And we could continue. But you can start to see that what we're doing is we're going to be moving in generally this direction. So instead of, say, something like Dijkstra's, which would basically be doing a BFS, which would consider all of these nodes, and then all of these nodes, and then all of these nodes, and all of these nodes, which would be, I don't know, 4, 9, 16. It'd be over 100 nodes to consider. What Astar will do is, using the heuristic function, will basically generally move in this direction. Now, it might consider a few extra nodes, as it did in that case. So it's going to start by considering all of these, and then we'll consider all of these, and then probably all of these, and then probably all of these. So it's not perfect. It's not going to find it in the very least amount of steps possible, because if it could do that, then we wouldn't need a search algorithm. We'd already know the answer, but it's going to do a pretty good job. And it's going to generally be moving in this direction, so it might only take 20-ish iterations. Sweet. Next, we're going to go through an actual coding implementation and use Astar. And so what we're actually coding up here is the 8-tile game, which is a game. It's a game like this where you're trying to move the tiles around in a fashion to be able to achieve some goal state. So in this game, we're going to denote a board game state as a matrix, and basically a node is basically going to be a matrix with a couple other things, but mostly it'll just be a matrix. And so this will be a state, and if we move the tile left or right, basically what we can think of it as moving this blank space up or down or left or right, and that will be a transition. Now all of the edge weights will have an edge weight of 1. So equipped with that, let's look at the code. Now I've tried to keep the Astar as generic as possible while also being able to be simple, which are sometimes conflicting goals, but this is the best I could do. So we have a node which contains the matrix for the board, and it's going to have a parent, a cost, and a depth, which both start at infinity. Now we are going to be able to calculate, okay, so we also have a priority queue here, which will always keep the item with the least amount of value as the highest priority. If you can think about it, if you have a to-do list and you have them labeled 1, 2, and 3, and 4 as your priorities, you would want the one that's labeled number 1 to come up to the top. So how we can do that is just by implementing this thing called a priority item, which is going to use the cost and the depth to make a comparison. And so then we're going to implement 2 various type of heuristics. So the first is called the misplaced tile heuristic, and it counts a +1 to the cost, the heuristic cost, if any item in the, it will compare 2 matrices and see basically for each entry in these matrices, if you look at the same entry in both matrix, if they're not the same, then add 1 to the cost. Now remember, the heuristic is supposed to be, if it's less, that's supposed to be an indication to us that we're moving in the right direction. Now the Manhattan distance is, I think it will become pretty clear that's the better cost. It's more informative. So it looks and basically looks through all of the rows in the matrix and sees how far is it for, let's look at this one. So it goes through matrix 2 after we've done some pre-processing and stored where all the values are in the first matrix, and it goes through the entries in the second matrix, and it sees how far is it, so say the number 1, how far is it to the number 1 in the original matrix coordinate dictionary. So if the number 1 is on opposite ends of the board of the tiles, then the Manhattan distance is going to be very large. And uniform cost is just the dumb return 0 cost. So here's the actual Astar algorithm, and we have some functions built in here. So this convert to nodes is just going to take a list of matrices and convert them to nodes, which remember the nodes we have up here. And update neighbors is going to take a basically going to be that middle part of the Astar algorithm that we're looking at. Look through all the neighbors. If the new depth, now we have a +1 here. Now if you remember the pseudocode, it was the current depth plus the distance between our current node and the next node. But in a game like this, all moves are considered of cost 1, and so we just have hard-coded the number 1 here. We look at the new distance and see if it's less than the distance to that neighbor. If so, update the neighbor's parent to my node, and the depth to update that as well. And if it's on the to-explore list, add the neighbor to the to-explore list. So we're going to look at the priority queue. We're going to create a priority queue. We're going to add the start node to the, priority queue. Now we're keeping a graph here. Remember how in the pseudocode we had basically a graph structure that kept track of all the nodes that we've seen before and what their distance was. Now generally, maybe in other applications, you might pass in the graph. So why are we building it dynamically here? Well, because remember how I said the nodes of a game like this can grow exponentially if you're considering all nodes, or actually combinatorially, based on a combinatorial explosion. And so we don't want to store every possible configuration of the board. We only want to store the configuration of the boards that are relevant to us, that may be adjacent to ones that we'd be interested in. And this is while true, if the to-explore list is empty, then that means that we have not found the goal state. And remember, if the goal state was findable, then that means we would find it. So I could write here instead of failure that this means that the goal state was not, this problem is not solvable. Okay. Now we're going to pop the first item from the list and see if it's equal to the end state. And if so, then we can return. And if we're going to turn all of the neighbors, we're going to look at all the adjacent matrices of the neighbor, which the adjacent matrices are, remember, if we have that tile board, then where can we move that blank piece of that tile? So in this case, this is an adjacent matrix to the initial matrix, because this is one where we just moved the blank tile over one. Okay, so then we're going to get all the adjacent matrices, convert those to nodes, and update the neighbors, and count +1. That is the Astar algorithm. It will exit when either we have reached the end of possible explorations, in which case there's not a solution to the problem, or we have reached the end state. And below here, we've just implemented some of these functions. I don't think they're super relevant to Astar, so I'm not going to drill super into them. This one gets the adjacent matrices, and this one moves that empty tile in a matrix. So next, I'm going to go through what happens when we run this, and we're going to look at the difference between what makes a good heuristic and a bad heuristic. Okay, so here we can see the comparison between when we use Astar to when we use a good. Okay, so here we can see the difference between heuristics on the the 8-tile problem. You can see on the right-hand length of how deep the problem is. So how many moves does it take optimally to solve this 8-tile problem? So as we move from 0 to 25, the problem gets harder and harder. Maybe at this 0 or 1, we only need to move the blank space 1 to achieve the end state that the problem is asking us for. Now, as we move to the right, you can see that all 3 of these graphs do get larger. However, some get larger very much faster than others. On the right-hand side, you get this is the algorithm iteration. So how many iterations the algorithm takes to find the optimal path. And so as you can see, uniform heuristic, which remember is basically Dijkstra's, and if in the case that it's all edge weights are 1, then it's breadth first search, you can see that this grows extremely quickly, basically combinatorially explosion. And this is, so if it would take 20 moves to solve this game, then it's going to take the algorithm 40,000 iterations to find that optimal path of 20 moves. However, you can see that the misplaced tile cost, which is a much better heuristic, it actually gives us information, unlike the uniform heuristic, which doesn't. The uniform tile cost takes less than 5,000 moves in a problem that can be solved with 20 moves. It takes less than 5,000 iterations to find that, which is obviously very good. But even, or much better than uniform heuristic. But even better is that Manhattan distance that we talked about a little bit. And that should make sense because the Manhattan distance gives us the most information about how close we are to the final solution. And what's more is it gives us a hint about what direction we should move in to get closer to that final solution. So you can see that the Manhattan distance really hardly takes any moves or iterations as compared to the other algorithm, the other heuristics. All the same algorithm, all A*, different heuristics. A better heuristic gets you the solution in a lot faster time. Now again, you will get a solution with no matter what heuristic you use. You could use, but how fast you get that solution, and that's what A* provides. Now I don't write how long these solutions take. Maybe I should have, but just I can kind of tell you that solving this at 40,000 iterations on my machine, took maybe a couple minutes. So it's not trivial. These things do grow very quickly, and so especially if you're looking for some sort of real-time solution, like maybe a robotics planner, then you need to probably think about what kind of heuristic you're going to use to really make this as efficient as possible. Well, that is a wrap for us today. I really hope you enjoyed this video lecture. If you are interested in learning about other algorithms, other topics in math, computer science, or statistics, please let me know. I'm just getting started, but I love to teach these things and connect with you on it and learn from you as well. So thank you. Please do like and subscribe, because I guess that's the thing you got to do on YouTube. But see you next time. Bye.